Thanks a lot for the invitation and also to the organizers for organizing this wonderful workshop. And well, if somebody has a question, you can interrupt me, of course. And also, if you ask it through the chat, I cannot see the chat because I'm full screen. So somebody let me know. Well, as the title says, I will be speaking about hydrodynamics somehow in the case of some kind of fluids which are integrable by means of a Morse-Bott integral. First, I will introduce a little bit the topic and theorem, which was kind of a milestone to topological hydrodynamics, which is Arnold's theorem. Then I will go into this theorem about realizing and classifying topologically these fluids. And at the last part of my talk, I will address another question, which is very related to it. So the Euler equations were introduced by Euler and model the dynamics of a fluid which is ideal. By ideal, I mean that it's inviscid and incompressible. Even though they were introduced in, of course, in the Euclidean space, they can be formulated in any Riemannian manifold and actually of any dimension, even though I will be speaking about 3 dimensions in this talk. Well, these are the equations where basically the x is what models the velocity of the fluid, of the particles, and p is a scalar function, which is called the pressure. Of course, if we are in a Riemannian manifold, all these operators are taken with respect to the metric, no? And here's a picture of Euler. This is something that my advisor Eva Miranda does a lot, and I like it, which is putting pictures about famous people you're speaking about. So I will focus on steady flows, and this is because behind steady flows there is much more geometry involved. And so when you focus on steady flows, there is a very nice formulation for the equations, which is much more appealing for us. I mean geometers. We introduce alpha, which is the dual form to x. If you want, is through the musical isomorphism induced by G. And then you introduce a function which is called the Bernoulli function, this little b, which depends on the pressure and the norm of x. And then the steady Euler equations can be equivalently written in this form, where here mu is the volume induced by the Riemannian metric. Okay. What happens is that the behavior of the fluid will depend very much on this Bernoulli function, and this is captured by the fact that this function is an integral of the vector field, a first integral, which means that the vector field is tangent to the level sets of this function. And this kind of dichotomy will be captured by Arnold's theorem, in fact. So another vector field, which is very important for these equations, is what's called the vorticity vector field. And this is a vector field which is uniquely determined by this equation in here. So it depends on the volume and d alpha, where alpha was the form dual to x. And this vorticity vector field, what it satisfies is that it commutes with x in the usual sense, and it is independent from it in the regular points of the Bernoulli function. Okay, so this tells you that, well, this already introduces this dichotomy that if if the Bernoulli function is constant, then it doesn't have any regular point, and the vorticity is everywhere parallel to x. This is what it's called a Beltrami field, and it's a particular solution, a particular steady solution to the Euler equations. Otherwise, if B is generic, let's say analytic or Morse-Bott, or with critical points of zero, critical level sets of zero measure, then you get that almost everywhere your vector field commutes with another, which is the vorticity vector field. So this is what actually Arnold's structure theorem, it's called like this, is telling you. No, in his original formulation, the hypothesis is that the Bernoulli function is analytic. Then let me denote by C the critical level sets of the Bernoulli function, and then what this theorem is telling you is that almost everywhere you have invariant tori. Okay, and then, well, in each of these tori, you have that the flow is conjugated to a linear flow, so it looks very much like a Hamiltonian system of 2 degrees of freedom. Okay, and this is actually going to be very important in this talk. So as I was telling you, in fact, this theorem applies not only in the analytic case, but as long as the smooth function is somehow nice, in particular Morse-Bott. To get a picture of what's going on, well, as I was telling you, your manifold can be split in some domains, three-dimensional domains that I will denote M sub I, and you have fibrations by invariant I or invariant cylinders if your manifold had boundary, because then you, well, yeah. So in the boundary, you get these circles in the boundary of the cylinder. So the main question I will be addressing here, or one of the main questions, is the inverse problem to Arnold's theorem, because of course Arnold's theorem is just telling you if you find a solution with a certain Bernoulli function, then blah blah blah, something happens, there's a rigid behavior, etc. But of course one could wonder like which functions can be actually found in steady solutions to the Euler equations for some metric. So I'm not fixing the metric anywhere in this talk. Okay, which is also very important because otherwise it's very difficult to find solutions. And a historical note, which actually I discovered much, well, later after finishing this work, is that this problem was actually already suggested by Dennis Sullivan a long time ago in 1994. And the other question that I will be addressing, which is very, very related to the first one, is so this was a question posed by Daniel Peralta Salas in 2016, which is maybe can we find certain three manifolds where you cannot find solutions of a certain type? For instance, solutions where the Bernoulli function is Morse-Bott or is analytic, or like, can the ambient space have some influence on these questions? No? And as I was telling you, I will address these questions in the Morse-Bott case. And the first one, I will completely answer it when X is non-vanishing, so you don't have stagnation points. So let me call, just to simplify, if X is a non-vanishing solution with a Morse-Bott Bernoulli function or an analytic, let me call this an Arnold fluid, okay? Then there's a theorem which actually has been proved in several points in the literature that already tells you that if X is non-vanishing, which is an hypothesis I'm taking right now, then you know that your ambient manifold cannot be any three manifold. And this actually was proved first by Fomenko and Matveev in 1988, and then has been reproved or mentioned in several other points, for instance, very recently by Chilevak and Volkov in this concrete context of Euler flows, okay? And so for those who are a bit familiarized with three-dimensional topology, these graph manifolds or manifolds which are constructed by gluing Seifert manifolds along their boundaries, okay? So for example, an hyperbolic manifold is not a graph manifold, to have an example of a non-graph manifold. Then as I was telling you, this Arnold's theorem is an a posteriori consequence. So if you have a solution with a certain Bernoulli function, then something happens. But actually, there is not so many examples of fluids in this hypothesis. And in fact, the only ones that I know are only in the three sphere and in the three torus with the round and flat metric. And this was, for instance, an example studied in a paper by Kessing-Kutzin and Peralta Salas. Well, yes, during the talk, I will be trying to let you know what we can discuss in the discussion session if you're interested in it. So for instance, I can tell you a little bit of geometric intuition between this theorem. So what we will first prove, and this is the proof I will detail better, I would say, is this theorem one, which is telling you that actually any ambient space can be realized by an Arnold fluid. Actually, this theorem is a weak version of one that I proved that I also will state, but this is easier for me to explain because I don't need to introduce a whole theory of Fomenko's Bott integrable systems. So this is what I'm telling here, that when you combine the methods to prove theorem one with this whole theory of integrable systems in symplectic and Hamiltonian dynamics, then you get a stronger version, which is actually that any, let's say, non-topologically obstructed Morse-Bott function can be realized by an Arnold fluid, okay? So this completely answers the inverse problem in the non-vanishing Morse-Bott case. a corollary of this is that all the invariants that were developed in the framework of Hamiltonian integrable systems actually also classify these fluids. Finally, and this I won't be explaining this, but it's just a very an observation that follows from it, is that you can find a way to simplicize this construction so that you find in Hamiltonian systems for a certain symplectic form of any topological type. This is something that Fomenko and I think, was it Borsinov, Fomenko, and Matveev already proved, but we get it with an extra property, which is that actually the vector fields are stable Hamiltonian rep fields, in case you know what that is. Okay, so for the constructions, so now I will be trying to explain how to prove theorem 1, and a lemma which is actually classical, but well, it was recently proved also in a paper by Daniel Peralta Salas, Ana Reichman, and Francisco Torres de Lizaur, is that, well, if in fact you don't need to be constructing metrics in your manifold, and you only need to look for one forms, because if you find your a one form which is positive on your vector field, and also you know that your vector field is volume preserving, then you can find a metric for which this alpha is the form dual to X. Okay, so that this simplifies quite a lot my problem, because then what I only need to construct in my manifolds are volume preserving vector fields and one forms that satisfy the first Euler equation, and that's it. So once I have this, I can find a metric such that the Euler equations are satisfied by this vector field. Okay. So let me first show you how to construct an Arnold fluid in a Seifert manifold. So Seifert manifolds, in case you don't know the definition, it's just three manifolds that can be foliated by circles, which again, it's not all manifolds. Okay. So what happens is that Seifert manifolds are very well studied and they are actually classified. And this classification is what I will be using to decompose it in simpler blocks somehow. Okay, and so what you do is you first start with so the way to construct the Seifert manifold is to start with a trivial S1 bundle over a surface, a closed surface orientable with some boundary components. And then to each of these boundary components, which are tori, you attach either a solid torus via den twist, or you attach the unit cotangent bundle of a Moebius band. So what you do is in each of these three different blocks, which are very easy to express, you construct an Eulerizable flow, so an Arnold fluid with a Morse-Bott Bernoulli function. Then the problem, of course, is that once you glue back your manifold, these fluids that you constructed will not match probably, especially when you are doing a den twist that is not trivial. And then what you need to do is to interpolate between these two fluids while keeping a control of the singular set of your Bernoulli function, so that it's still a Morse-Bott function. And this is what I call the interpolation lemma, which is the main point of the construction. So let me picture it so that you get a very nice image of what's going on. So you start with this surface. It might have as much genus as you want, as much boundary components as you want, but this is an example, times S1. And then in some of these boundary components, you attach solid tori via some den coefficients, okay, with a den twist. And in some others, you attach this unit cotangent bundle of the Moebius band with actually with somehow a trivial surgery. There is no twist here. Then in each of these gluing locus, the neighborhood is just diffeomorphic to thick torus. And in there is where you apply the interpolation lemma, which is this, well, I just stated here, but I won't be proving it. But this is just telling you that you start with two linear flows in the boundary of this thick torus. And then in between, you can find a one form such that the Bernoulli function has no singular points. So that if it was Morse-Bott in each of the blocks, it will still be a Morse-Bott function. with this, we finish the construction of an Arnold fluid in a Seifert manifold. And then to get the construction in a graph manifold, one just needs to adapt a little bit the interpolation lemma in order to glue Seifert manifolds with boundary. Because in that case, basically, your Morse-Bott function will have an extra singularity, maybe, because it might happen that they are both decreasing in the boundary component, so that you need to have a 0 or something like this. Okay, but I'm not going to state this, but it's just an adaptation of the interpolation lemma. And this proves that you can find in every graph manifold an Arnold fluid with a Morse-Bott function, Bernoulli function. In order to obtain the analyticity, which I was stating also, you need to use a theory by Sciotta, quite old already, and which basically gives you enough conditions for a function to be analytic in suitable charts. And then you check that your Morse-Bott function satisfies this. So this proves theorem 1. As I was telling you, to get the more general result, you need to combine some of these arguments with the theory of Fomenko et al. And you need to check that actually this theory of Fomenko applies also in this context and so on. And this is something that can be discussed in the discussion session. Let me now address the last question that I was introducing. So right now, once you construct this using Fomenko's theory, you obtain a classification of Morse-Bott integrable fluids, which are non-vanishing. Now, let me allow my fluid to have stagnation points, okay? And actually, if you look at the Euler equations in here, you will see that if my Bernoulli function is Morse-Bott, x can only vanish in the singular points of my Bernoulli function. So now I'm covering indeed more fluids, okay, now that I allow to have stagnation points. In this context of, as I was telling, the Morse-Bott Bernoulli function can be much different, because you can have now, for instance, critical strata of dimension 0. You can have non-degenerate critical points, but not only this, something else can happen, because now in your critical circles, there is not necessarily a non-vanishing vector field, so that somehow the topology around of the foliation induced by the Bernoulli function can change. Okay, so now a natural question, because now the theorem that was telling you that it has to be a graph manifold does not apply anymore. And then what you can ask is, well, can we find actually a Morse-Bott integrable fluid with stagnation points in non-graph manifolds? And the answer turns out to be no. So this also, let's say, completely answers the question that which ambient manifolds can have a Morse-Bott integrable fluid in the general case for any metric. This is a topological obstruction, as I was telling you. And for instance, the hyperbolic manifolds are examples of non-graph manifolds. And also, if you know a bit about three-dimensional topology, if your manifold has one hyperbolic component in your geometric decomposition, then it's not a graph manifold also. And the sketch of the proof, again, we will use the theory of Fomenko, but of course it does not apply, let's say, immediately as before, because the theory of Fomenko and his collaborators was always applied in regular level sets of Hamiltonian functions, where your vector field is non-vanishing. In our case, we do have some stagnation points, at least a priori. So what they did while studying these graph manifolds and so on was showing that, they introduced this concept of a tame function, which is a function which is not necessarily Morse-Bott. Actually, it can be smooth, but it has a very nice or controlled singular set. So the assumptions are the ones that are written here, that every regular set is either a torus or a sphere, and the critical level sets are stratified. The critical points only lie in circles or closed surface of non-negative Euler characteristics. And something that it's rather easy to obtain is that if I suppose that I have an Arnold fluid with a Morse-Bott Bernoulli function, then this Morse-Bott Bernoulli function if it does not have isolated critical points, then it's a tame function. Okay, so if I assume that my Bernoulli function has only circles and surfaces which are critical, then it's a tame function, and this follows from Arnold's theorem actually, because if you have a critical surface in the neighborhood, it has to be foliated by tori, by regular tori, so that this surface has to be either a tori or a Klein bottle actually. So at the end, what you need to prove is that, well, what you deduce from this theory is that if we could find a Bott integrable fluid in a non-graph manifold, it has to necessarily have an isolated singular point. By isolated, I'm just meaning a non-degenerate point, a Morse point, okay? Because if not, it will be a tame function, and the manifold will be of graph type. Because this is what Fomenko and Matveev proved, that a tame function can only exist in a graph type manifold. So to conclude, and this is the final proposition, is that one can prove, and this is holds in general for any metric and for any Bernoulli function, there cannot be a non-degenerate critical point in a Bernoulli function. And this concludes the proof, because if you cannot have a non-degenerate critical point, then your Bernoulli function would be a tame function, and your manifold has to be a graph manifold. Okay. This proposition also can be discussed in the discussion session, but there is one case which is very easy, and I can already tell you how to prove it, which is that there cannot be a maximum or a minimum point, because then by Moore's lemma, in the neighborhood, the regular level sets are spheres. And this contradicts Arnold's theorem, because Arnold's theorem is telling you that regular sets have to be tori. The only case which is a bit more complicated and that uses strongly the Euler equation is the saddle case, saddle points. Now let me finish just with some references. These first references are about topological hydrodynamics. Here, the first paper is where Arnold proved his structure theorem, well, the French translation. Then there is this monograph by Arnold and Kessin, which is the main references in topological hydrodynamics, and the course that Daniel Peralta Salas wrote, where he was asking this question about obstructions, like ambient manifolds which are obstructed. And then some of the work I've been doing in my thesis, which is using topological and symplectic methods, let's say in this analysis of steady Euler flows. This is the paper I was speaking about today, and some other two papers about futures of higher dimensional Euler flows, one with my PhD advisor, Daniel Peralta, and Francisco Presas, who are collaborators from Madrid. And now, Cedric already told you, I'm going to do a little bit of advertisement about next year, which this workshop is going to be held in Barcelona. So I very much encourage you to come, hopefully live and not online. And this is the link. And thanks a lot for your attention. Let me also thank again the organizers, since it's the last speak. Thanks a lot for everything and to listening.